Hello everybody, welcome back to this channel. I hope you enjoyed the first few lectures. Although it could be confusing at some point, I hope you understand all the concepts. So today we're going to cover the last topic in chapter 8, which is the power associated with the steady-state sinusoidal signals. And I have some noise probably going on because there are some construction work is being done in the neighborhood. I apologize for that if the mic picks up that noise. Let's get on to the topic. So today I want to talk about the instantaneous power and the average power and the maximum power. Let's look at the first one, the instantaneous power. So let's see here. I have a box representing a circuit inside this. I don't really know what it is, and I have the current I and V labeled. So these currents IT and VT, they are all instantaneous. And the time varying, of course. And first thing is the passive sign convention followed here. So how we can tell whether the passive sign convention followed? And we're looking at whether the arrow going into the plus sign of that reference, the voltage reference mark, right? So let's see. Here it appears not, because it looks like going away, but here this VT is same as here, right? So therefore the passive sign convention actually is followed here. Okay, once the passive sign convention followed, and we can definitely see the power delivered to this circuit, to the circuit in this box here, would be the VT times the IT, or IT times the VT, not a B, right? So that's the value of having the passive sign convention. If the passive sign convention is not followed here, and in that case the power delivered to the circuit would be negative VT times the IT. Right? I hope you really get this concept, although seemingly simple, but very important. You get the concept really understood. Okay. So let's look at a few instantaneous power for the different elements. So the first one is the instantaneous power delivered to or absorbed by the resistance. So here I have the current source I sub t, and I have VR sub t. So therefore the VR, we know that from the element constant. By the way, the IT and V sub RT are following the passive sign convention, right? Because the current is essentially going into the positive terminal of the voltage reference mark. And so therefore VR, excuse me, VR is going to be equal I sub t IT times the resistance. So the P, the power absorbed by instantaneous power absorbed by the resistance, would be just equal IT times VRT, and that's equal IT squared times R. And if I have the current given in this form, and that would be equal to, if I substitute this I sub t into this equation here, that would be equal to, let's see, I sub A, which is the amplitude of that sinusoidal signal. By the way, this I sub IT in this case is in steady state, right? So the amplitude I sub A, that means will be constant. The omega angular frequency will be constant, and here phase angle is 0, of course it's constant. So that's I times the cosine omega t, and the square times R. And if we use a trigger identity, cosine x squared equal half 1 plus cosine 2x, you do not need to memorize these, right? Not to remember. You don't need to memorize it. I have Appendix B. I call the trick to trick. You can check that out and see how easy you can get this trigger identity. I mean, you own these trigger identity. You don't have them in your text. You don't have them in some references. This become part of you. Okay. So in this case, I can write the equation. So in this case, I have I sub a squared times r times the cosine omega t squared. I replace that by half 1 plus cosine. So in this case, I'm taking this as x, right? So cosine 2x, which is 2 omega t. So this is the power. Yeah, if I write this, if I separate this to two parts, I have half I sub a squared times r plus half I sub a squared times r times the cosine 2 omega t. This is a very interesting part. This is DC component. The things doesn't change over time. And the other term, this variant, this is a 2 omega term. And this actually is very common to any single phase. We're gonna talk about it in the very end of this course. Maybe lecture 30, something like that. We talk about 3-phase, and we also have single phase. So the single phase system, this is very common. You will have what we call the 2 omega term, and the 2 omega term is sometimes very hard for the designs. If you do the power electronics, in the single phase, because this 2 omega term, that will make the DC link voltage kind of rippling at the low frequency, no matter how high the switching frequency is. So we have different ways of dealing with that, and I have patent on that. But anyway, so this is the kind of interesting part. Pay attention to that. So this is the 2 omega term, but this of course is AC, right? AC, pure AC, because this varies between positive and negative magnitude of half IA squared times R. Let's look at the inductance. For the inductance, the voltage V sub L is equal to L times di dt. And by the way, in this case, I sub it and V sub LT are following the passive sign convention. That's why we can put L times without any negative sign involved. So in this case, we assume that I would have the same current as we had for the resistance case. And in this case, we would have, based on the trigger, the derivative, so d cosine x dx equal negative sine x. And based on that, we treat the omega t as x. So in this case, we can get L times d dt IA times cosine x, right? And then in this case dx, and then we need to do the derivative of x with respect to t again. So in this case, we have negative sine x. So I have IA is a constant, so I have negative L IA sine x is omega t, so I put omega t back, and the dx dt is omega times the omega, so therefore I have negative omega L IA sine omega t. And if I do the instantaneous power, so therefore P sub LT is equal IT and V sub LT. So IT, we substitute that back to, so in this equation, we have negative omega L IA squared, because I have IA here and also IA from IT. and therefore I have sine omega t and cosine omega t. And then using the trigger identity, we have sine x cosine x is equal half sine 2x. We can rewrite this one as negative half omega L IA squared times sine 2 omega t. Right. Again here, this is the only, so this is 2 omega term, but this is AC only. Right. So this is different from the resistance case. For the instantaneous power of the resistance, you also have that constant DC part. Let's look at the capacitance. For capacitance, we have voltage source connected to, applied to the terminal of the capacitance, and we have capacitance current. Based on what we learned in the 201, the I sub C should be equal C dV dt, the voltage across the capacitor, in this case the V. And this equation is correct if the voltage and current are following the passive sign convention. Right. So in this case, I substitute this. I can do the similar thing I did for the inductance. I'm not going to go through the details. So in this case, the solution would be negative omega c times the VA times cosine times sine omega t. Right, so the instantaneous power delivered to the capacitor or absorbed by the capacitor is P sub C T is, by the way, I use the lowercase p for the instantaneous. We're going to keep the uppercase p for the average power. P sub t, in this case, this is, so that's Vt times I sub Ct, which would be equal negative half omega c and Va squared times sine omega t cosine omega t. The same trigger identity will give us half omega c Va squared and sine 2 omega t. So again here, this only AC term at the frequency of 2 times omega. Right, so that's for the instantaneous power. So next we're going to look at the average power.